Okay, I think we can get started. Let's give it some number of seconds for people to trickle in. Okay, good. Okay, cool. Welcome to lecture 18 of Digital Design and Computer Architecture. Today, we're going to continue a fascinating topic, branch prediction, that we started last time. We'll see how much ground we will cover. There's a lot that has went on branch prediction, and people have come up with many, many exciting and interesting algorithms, as we will see today. I intend to at least get to the point where I give you something close to the state of the art, which you can think about, but hopefully it'll be exciting. Okay, remember, these are your readings. Somehow, okay, these are your readings, and hopefully you've done a lot of it, especially if you've done the last one, McFarlane's Combining Branch Predictors paper. This will cover a good chunk of today, until the point where we will discuss hybrid branch predictors. Okay, let me make sure this is okay. Okay, good. Okay, and after we're done with branch prediction, not today probably, we'll jump to other execution paradigms where we will cover VLIW, which is heavily impacted by how we handle branches actually at the compiler level. And then we will cover systolic arrays and decoupled access and execute. This will probably happen tomorrow. And then next week, we will cover SIMD processing and GPUs. And then we will go into the memory hierarchy. Okay, remember we were covering how to handle control dependencies. Branch prediction is just one way of handling the control dependencies, but it's an important way. And we've already covered stalling the pipeline, not a good idea. Doing something else, fine-grained multi-threading, which is a good idea under certain circumstances. We'll see it again in GPUs. And we were covering branch prediction. And if time permits, we're going to cover some of the other techniques as well. And remember the slides where which I showed you to motivate the branch prediction problem. I'm not going to go over it again, but it's good. We're going to do this exercise later on today again, but with some assumptions that we have discussed last time. We did the math. And if you have only a 60% accurate branch predictor, you execute essentially 800% extra instructions that you're not supposed to fetch if you were 100% accurate. And your program, instead of taking 100 cycles, it takes 900 cycles. So you basically lose 9x. Your performance basically goes down by 9x, let's say, which is not good, clearly. And this is 60% accurate. 60% is better than random luck, right? And we're going to see that today's branch predictor is actually much higher accuracy than 60%. Because of this reason, basically, we don't want to waste performance and energy while we have deeper pipelines and wide fetch engines so that we can extract parallelism. Okay, so if you're 90% accurate, it's not enough also, actually. You can see that we fetch 200% extra instructions, and our performance compared to the ideal branch prediction becomes 3x worse. Okay, so we want actually better than 90%. And recall, this is what the fetch engine of a modern processor looks like to predict the branches. We're going to build on this essentially because this is important. Essentially, we have a cache of target addresses. This is called the branch target buffer. This stores a target address associated with a program counter, meaning a branch, after at least it was executed once. So you basically execute the branch once and store the target address so that next time you know the target address by accessing the structure without really computing the address again, because the address doesn't change if it's PC plus offset, if you remember. For conditional branches, address doesn't change in most ISAs, instruction set architectures. So this is going to be a fundamental component, this BTB. I'm going to refer to BTB, branch target buffer, in this lecture also. And that's essentially the target address cache, which the front end fetch engine indexes using the program counter to get the target address of the branch without computing it, because it has already computed a previous execution of the branch. Okay, and then we also have, basically, if you hit in the BTB, you have valuable information. If the program counter hits in the BTB, you get the target address. And you also know that this is a branch instruction because you've executed it once. Otherwise, you wouldn't have inserted a target address into the BTB for the instruction. And at the same time, concurrently, you need to make a prediction about the branch, direction prediction about the branch. Should the branch be predicted taken or not taken? And if it's predicted taken, then you take the target address coming out of the BTB. If it's predicted not taken, then you should really fall through. Or if it's predicted taken and you don't have the target address in the BTB for some reason, for whatever reason it might be, then you actually fall through, meaning go to PC plus 4 in MIPS, PC plus instruction size in the general case. Okay, so you need to have a calculator still, or incrementer of the PC still by the instruction size over here. And we talked about what happens if your instruction size is variable, etc. in the last lecture. Clearly, that complicates this fetch engine. And that's what we have in x86 today. But this is the complete fetch engine. And now we're going to talk about how to build this direction predictor, essentially. And we have actually been talking about how to build this direction predictor, except that direction predictor has been compile time so far. Remember, we talked about the basic prediction mechanism, always not taken. In fact, we talked about it when we built the pipeline processor, not even in the last lecture. We talked about always taken prediction, backward taken, forward not taken prediction, compiler-based profiling, and program analysis-based prediction. So these are all static prediction. What does this mean? Basically, they do not change their decision based on dynamic events that occur during runtime. In other words, this direction predictor doesn't get updated. You can store the directions in some way. They could come from the hint bits in the instruction. If you remember, there's a single hint bit saying, if this bit is set to 1, the branch is likely taken. If this bit is set to 0, the branch is likely not taken. So based on that, you make a decision. And that bit is set by the programmer, by the compiler, and as we discussed last time. And it could be set cooperatively also. Remember, I left you with the question, how should this bit be set if you have different kinds of information coming from the programmer, compiler, and the profiler, maybe the dynamic profiler also. Okay, but we're not going to go into compile time. All of these compile time mechanisms have one downside. If the branch changes behavior dynamically, meaning that if the branch doesn't always have a very likely direction, for example, if a branch is 99.9% taken, then identifying that at compile time is good because you're not going to change that direction much, assuming that you identify correctly, of course, right? You have a representative input set, as we discussed. But if the branch is 50% taken and 50% not taken, and it basically has a behavior that's really predictable, these mechanisms do not do well because you have only a single bit to encode the information, and you cannot get more information to actually change that bit, unless you have a dynamic compiler, as we discussed last time, but that comes with other overheads. That's why we motivated the runtime dynamic branch prediction, and we're going to go into dynamic branch prediction heavily today. Essentially, everything we will cover today will be about dynamic branch prediction. But keep in mind that compile time branch prediction can complement dynamic branch prediction for branches that are really, really easy to predict statically, either programmer-based or compiler-based. Okay. So we're going to look at many algorithms for runtime dynamic branch prediction. And the simplest one is going to be last time prediction, as we will see. Okay, so the idea of dynamic branch prediction, as I already said, is to predict branches based on dynamic runtime information that's collected at runtime. So this has advantages and disadvantages like any idea in computer architecture. First of all, the advantage is you make your prediction based on the history of the execution of the branches, based on what you learn, what you memorize or learn over time, as we will see. Basically, this enables the machine to adapt to dynamic changes in branch behavior. If a branch is taken, first 50% of the execution, and then changes behavior, it becomes not taken in the remaining 50% of the instances, you can easily identify this dynamically, right? Whereas you cannot do that if you have only a single bit saying this branch is likely taken or likely not taken. And also, it gets rid of the static profiling problem. Basically, input set representativeness problem that's associated with compilers or the programmers goes away, essentially. You don't need to profile the code because you are looking at what's happening during the execution of the real program with the input set that the real program is given. You don't need to come up with a collection of input sets that are representative of general input sets because you're really doing this, making this decision based on what's really happening in the actual program and actual input sets. So this is a big advantage, clearly, with dynamic branch prediction also. But of course, it will come with extra hardware cost. And we will see that we're going to increase complexity actually significantly. We're not going to quantify that complexity. That's certainly you could do, but we don't have time for that. But you will see some of the algorithms that we will discuss will require significant complexity in hardware. And keep in mind always that more complexity is just hardware complexity, of course, hardware cost, but it's also latency. It can add latency to your fetch stage. If the latencies are too long, it can affect your critical path. Of course, you don't want it to affect your critical path, and you divide the branch prediction latency into multiple cycles. But once you start doing that, your fetch stage becomes multiple cycles also. So your pipeline becomes deeper. And a deeper pipeline increases the branch misprediction penalty and also data dependence handling penalties, etc. So basically, you will need to deal with the latency implications of branch prediction as well as you make it more complex. But today's branch predictors are quite sophisticated, so they can make predictions in multiple cycles, and we're going to talk about that as well. Ideally, you would like to make the prediction in one cycle, of course, so that you can get it, and you can predict the next fetch PC at the end of the cycle, so that you can fetch the next instruction using the next fetch PC. Okay, so let's talk about the last time predictor. This is the simplest of the dynamic branch predictors, and as you guessed, the idea is very simple. You basically predict. You execute the branch many times, of course, right, while the program is executing. The next time you fetch the branch, you predict the direction of the branch as a direction that was that the branch went the previous time it was executed, in the previous instance, actually. Basically, a branch executes many instances. You know what happened in the previous instance when you executed the branch. And when you fetch the branch, you basically use that previous instance's direction, taken or not taken outcome, as your prediction. And the assumption is that last time the branch was taken or not taken, this time we're going to have that sort of behavior again, right? Well, of course, this may not be true, right? Okay, so let me give you an example. So for this to be able to work, you need to have a single bit per branch. And that bit indicates whether the branch was taken or not taken the last time it was executed by the machine, resolved in the branch execution unit, right? And you store that information into the direction predictor, which could be part of your branch target buffer, as we will see. And this bit indicates which direction branch went last time it was executed. So let's take a look at a history of a branch that looks like this. Basically, I'm showing you the execution history of a branch. 10 times it was taken. T means taken. So for the first execution, first 10 execution, it was taken. For the remaining 10 executions, it was not taken. And imagine that this is done in a loop. So you basically execute the branch 10 times, it's taken. 10 times it's not taken. And then later you execute some other things, and then you go back to this loop and you re-execute the branch. The first time it's taken, 10 times it's taken. The next 10 times it's not taken. And then you go back and come back to the loop again. Let me try to annotate this with my little annotator thing here. I guess Spotlight could work. Okay. Yeah, so basically these are the taken outcomes and these are not taken outcomes. And we're going to analyze the accuracy when you go back to the beginning of the loop. So basically, you can see that in the first 10 outcomes, you're going to predict the branch as taken because the previous execution was taken. Ignore the first one over here. We're going to get back to it. You're going to make a mistake only when branch switches direction, right? So in the last execution over here, if you look over here at the 11th instance, when you're fetching the 11th instance of the branch, you're going to predict it taken because the last time the branch was taken. But you will see that when the branch is executed, it's not taken actually. So you will make a mistake. You will have to flush the pipeline. So you flush the pipeline only when the branch does something different from the last execution, last instance it was executed. So this is one instance, for example, over here. And the next instance where the branch does something different is when you, so this is at the end of this 20 iterations, let's say, the branch was not taken in the 20th time. Let's say you execute other stuff, and then you go back to the branch later on in the program because you're looping, let's say. Then when you start the loop, the branch is taken again, but you will predict it as not taken because the last time the branch was executed, it was not taken, as you can see over here. As a result, you will make a mistake. So you will make a mistake whenever the branch switches direction compared to the last time it was executed. In this particular case, you will get 90% accuracy because you make 2 mistakes in 20 instances of the branch, which is not bad, clearly, which is better than 50%, which would have been the case if you had only 1 bit indicating the likely direction. In this case, the branch is not biased, as you can see. You can only encode 1 direction, so you get 50% accuracy. So we've already improved the accuracy significantly, but we will see that we can do better. So basically, The upside is you improve accuracy, as you can see. The downside is you will always mispredict the last iteration and the first iteration of a loop branch, assuming this is a loop branch, because in the last iteration, you will do something that's different. And in the first iteration, you will do something that's different from the last time it was executed. Okay. So basically, accuracy for a loop with n iterations will be n minus 2 divided by n. Why? Because in the last iteration, you will predict the branch. So when you think about a loop branches are usually taken, as we discussed, right? Last iteration means you're exiting the loop. So you should really predict it as not taken. But you're predicting it as taken because the loop executes, and the last time you executed as not as taken. And when you come back to the loop at the beginning of the branch, last time you executed, you had exited the loop, meaning that you're going to predict it as not taken. But because you started the loop again, then you should really predict it as not taken because the loop is going to iterate many, many times, right? That's why the first iteration and last iteration are always mispredicted, and you can think about this a little bit more. So for accuracy for a loop branch with n iterations, n minus 2 divided by n because of this reason. Now, this is not a problem if n is large. If n is like a 1 million or 1 billion, right? You're iterating over, you have a lot of iterations in your loop. You're iterating over a large array, for example. Not a problem. You get close to 100% accuracy. Now, if your n is very small, like 2, for example, then you get 0% accuracy, right? 2 meaning you take the loop branch once. The next time you execute the, basically you execute the loop iteration once. The next time you get out of the loop. So basically you execute the loop once. That's the minimum number of times you execute the loop, assuming you go into the loop, of course, right? So basically for loop branches, for loops with large n number of iterations, this is great. But for loop branches, for loops with small n, small number of iterations, you get, in the worst case, you get this, 0% accuracy. So this is clearly the Achilles heel for this last time predictor, right? You take the branch. In every instance, the branch changes direction when it's executed. Last time prediction is the worst possible, well, one of the worst possible prediction algorithms that you can use for this type of branch, because the current instance of the branch will do exactly the opposite of the last instance of the branch. Last time it was taken, the current instance will be not taken. But you don't know that at the prediction stage, at the fetch time. So you predict it as last time, and you mispredict every single time this branch. So this sounds bad, right? It sounds bad because clearly we can see that this pattern looks very predictable, right? We're always doing the opposite of what we did last time. So if we had some more information, maybe we could predict this nicely. And we're going to build into that, basically. We're going to build into some simple ways of doing that, but you could also build some more information into the system. Okay, so hopefully this is interesting. This is the simplest prediction mechanism, dynamic prediction mechanism, last time prediction. But as everything, it has upsides and downsides, right? So we're going to try to fix the downsides while not affecting the upsides of it. So we will see next idea. But before we go into the next idea, let's take a look at the implementation of it. Implementation is basically what I showed you earlier. So this is the program counter. You index with program counter the BTB. You also index a direction predictor. And the direction predictor basically stores information about that program counter, about essentially what direction the branch at that program counter took. If it's taken, it'll be a single bit. If it's not taken, if it's taken, that single bit will be set to 1. Otherwise, the single bits will be set to 0. Now, what you can do is you can incorporate this direction predictor inside the BTB also, because you use program counter to access the BTB to get the target address. Why not also store the prediction inside the BTB? And this is what the slide shows essentially. So this is what a BTB looks like, branch target buffer. Basically, we use 1 bit per entry, per branch, if you will. And you can see that the BTB is accessed like a cache, as we will see later. But essentially, you use the BTB, you index the BTB with part of the program counter, and you use a tag to make sure that you actually have that program counter in the BTB. And if the address program counter exists in the BTB and the branch was taken last time, then we use the target address from the BTB as the next program counter. Otherwise, we use PC plus 4 or PC plus instruction size. Okay, so basically, this is one way of implementing it, and this is a way that the simple predictors implement in many modern machines. Of course, many modern machines use many other predictors as well, as we will see, but this is one of the predictors that they also use. And you can see that the 1 bit entry is updated with the correct outcome after each execution of a branch. So after you execute the branch, you update this plus the target address. Okay. Okay, so hopefully this is clear. Now let's take a look at the state machine for this last time prediction, because we're going to build a different state machine later on for 2-bit counter prediction, as we will see. But basically, the idea is very simple, right? You do what you did last time. If last time the branch was taken, you predict the branch is taken. That's what this state means. You use 1 bit to encode 2 different states. And if the last time branch was not taken, you predicted not taken this time. And if the branch is predicted taken, and it is actually taken, you stay in the state, right? Clearly. If the branch is predicted taken, but the outcome is actually not taken, then you change the state to 0 or predicted not taken, depending on how you encode it. In the encodings, we said 0 earlier, so I'm going to stick to 0. If the branch was predicted not taken in the fetch stage, but after you execute it, you figure out it's actually not it's also actually not taken, no problem. You did a correct prediction, you stay in the state. And if the branch is predicted not taken in the fetch state, but it was actually taken when it was executed in the pipeline, then you switch the prediction to predicted taken. And this is a simple 1-bit state machine. And you all know about state machines by now very well. You built state machines. And we're going to improve the state machine later on. Basically, the downside of the state machine is it changes its mind very quickly. Meaning, whenever it sees an opposing outcome to the prediction it has made, it basically says, oh, I did something wrong. So I predicted it's taken, but I see an opposing outcome. It's actually not taken. So I'm going to start predicting as not taken. And this may not be a good idea because the branch, that might be a fluke outcome, let's say, or that may be a case where the branch went not taken once and it's going to be taken again, right? Especially if for loop branches that execute a good number of times, that is the case actually, as we will see, or as you can guess also, right? Basically, the downside of this predictor is it changes its mind quickly. It just basically does exactly what the last instance does without looking at a longer history of what happened in the last few instances, let's say. And we're going to incorporate that longer history in the next predictor that we're going to build. And that's the idea we're going to look at right now. Basically, the problem, as I said, is a last time predictor changes prediction from taken to not taken, or not taken to taken too quickly. Whenever it sees an opposing outcome, opposing piece of evidence, it changes its mind. But maybe we should wait until we see more evidence as to whether we should change our mind for prediction. That's the idea. The reason is the branch may be mostly taken or mostly not taken, right? Loop branches are mostly taken. Whenever you see a not taken outcome, probably it's not a good idea to change your mind right away. Wait for some time to see if it's actually behavior that's going to persist for some time. Right? That's the idea. So the solution idea is very simple. We want to add hysteresis to the predictor so that the prediction does not change on a single different outcome. Now, hysteresis is a very common engineering concept. Whenever you design control systems, you want the control system to be stable, meaning whenever you see something happening, you don't react immediately. You wait and you react after you see, okay, after you see there's enough evidence that you should react. And my favorite example for this is air conditioning or heating systems, right? If you have an air conditioning system, you set the air conditioning temperature to, let's say, 20 degrees Celsius. And let's say the room is at 20 degrees Celsius right now. And it goes up to 20.2 degrees Celsius. Now, at that point, do you really kick in the air conditioning so that it would cool the room? Maybe not a good idea. You wait for some time to see if the temperature is actually really going up, right? You wait for some time and you see the temperature becomes 21 degrees. Do you really enable the cooling system to kick in at that point? Again, if you have hysteresis, you basically wait for some time, and that sometime is designed is built into the design by the designer. And the designer may say, okay, I'm going to wait until 21.2 degrees until I decide to kick in the cooling system. Otherwise, you may get into a situation basically where you kick in the cooling system reduces the temperature, and then you kick in the heating system, and then heating system increases the temperature, and you keep oscillating between them. And you're always consuming energy in the cooling and heating system, and the person in the room is not comfortable as well, probably, because the system is always operating in two different modes and switching its mind very quickly between the two different modes. Whereas if you build some hysteresis into the system, there's a region around 20 degrees, let's say between 19 degrees Celsius and 21 degrees Celsius, you don't do anything. But if you are out of that region, if you're out of that region at a higher temperature, you start cooling. If you're out of that region at a lower temperature, you start heating. And that's the idea, basically. That's the idea of hysteresis. You don't change your mind quickly, you wait for some time. And we're going to add that to the last time predictor. And the way we're going to add that is basically by changing the finite state machine to not have only a single bit, but have 2 bits. Basically, we're going to use 2 bits to track, and you can, of course, generalize the idea to 3 bits, 4 bits, 5 bits, 6 bits, m bits, right? Basically, we're going to use 2 bits to track the history of predictions for a branch instead of a single bit. Basically, we're going to look at last 2 outcomes of the branch. If last 2 outcomes of the branch are consistently, let's say, not taken, then we're going to definitely move into a not taken prediction. If the last 2 outcomes of the branch are consistently taken, we're going to move into a definitely taken prediction. Okay? That's the idea. And as I said, you can generalize the idea. If you want to add more hysteresis, you may want to add more bits, 3 bits, for example, and you may want to look at the last 8 outcomes, or 4 bits, and you may want to look at the last 16 outcomes. And then you may actually decide how to distribute the different states that you have in the m-bit counter. But 2-bit counter turns out to be very commonly used. 3-bit counters are also used, as we will see in one of the processors that we will discuss later on. But that's the basic idea. And let's take a look at how we do the 2-bit counter in the general case. There are many variations of it, but I'm going to show you a very common variation. Basically, we're going to have 2 states each for taken or not taken, instead of 1 state for each. And this was actually introduced by a seminal paper by Jim Smith in ISCA 1981. This is a major conference in computer architecture. And it basically made a huge difference. It increased the prediction accuracy significantly. As a result, it was the state of the art for at least a decade or so. It was employed in many high-performance processors as the major branch predictor, as we will see. So there's a question, aren't there always branches that will result in 0% accuracy for such a predictor? And yes, you can always construct some branch execution pattern that will lead to very poor accuracy, even with this predictor. But right now, we're talking about average branch behavior. So that's a very good question, basically. Average branch behavior turns out to be very amenable to this sort of hysteresis, as we will see in the loop branches. But yes, you can always construct a branch execution scenario where you can get 0% accuracy, actually. So I'm not going to go into that right now, but that's a good exercise also. Okay, so 2-bit counter-based prediction. Essentially, the basic idea is to associate each branch with a 2-bit counter, 2BC, I like calling it. Some people call it bimodal prediction. In fact, I think the McFarlane paper that I assigned you actually also calls it bimodal prediction. I don't like it that much, but that's fine. 2BC is fine. 2BC is much more descriptive, as you can see. So 1 more bit provides this hysteresis. And the key idea is a strong prediction does not change with 1 single different outcome. You wait for changing your belief. Basically, you wait for some evidence before you change your belief or thinking, essentially. If you think about humans, right, that's how we may behave also. We may want to have some hysteresis before, if you have strong evidence for something, we don't want to change that. We don't want to change our thinking until we see at least some strong evidence. We don't want to change it with a single opposing outcome. That's how science also works also. You don't change the theory based on a single opposing outcome, but over time things accumulate and you basically change the theory based on multiple opposing outcomes that are different. Okay, so this is basically counter using saturating arithmetic. Essentially, you have 4 states because you have 2 bits. And we're basically going to do arithmetic with maximum and minimum values because clearly the maximum is 3 over here and the minimum is 0. But now this is our state machine. And we have multiple states. We have 2 states where we predict the branch has taken, the blue states. And we have 2 states where we predict the branch has not taken, the red states, if you will. Now, you can see that if we somehow get into the predicted taken state, we're basically thinking the branch is strongly predicted taken. We need to see 2 opposing outcomes. Oh, okay, let me go back that way. Basically, this is the state where we are in. We need to see 2 opposing outcomes to actually go to a state where we predict the branch as not taken. Okay, so we're in the state. The branch needs to be actually not taken to go into another state where we still predict the branch taken, because this is a weakly taken state, if you will. And at that point, if the branch is actually taken, then we go back to the strongly taken state. Okay, basically, that's a case where hysteresis worked. We're predicting the branch taken. The branch is actually not taken. In the next instance, we're still predicting the branch taken because we have hysteresis like this, and the branch is actually taken. So we did the right thing in the next instance. So we go back to strongly taken again. So the only case where we change the prediction is when we see two consecutive outcomes that oppose the prediction that we made. So we predict the branch taken in the strongly here, and then it's actually not taken. We predict the branch taken again, weakly, and then the branch is actually not taken, and then we say, okay, maybe we should predict the branch not taken. And then if the branch is actually not taken, you go to strongly predicted not taken state. And it works symmetrically the other way also. If the branch is predicted not taken strongly, you need to see two opposing outcomes to go back to as predicted taken state, as you can see. So, okay, this is very simple. I've gone through a simple finite state machine, but these also have names, basically. This is a strongly taken state, where it's a strongly taken state is a state where you predict the branch and you don't change the outcome by one opposing. You don't change the prediction by one opposing outcome. Weakly taken state is a prediction state where you predict the branch and you change the outcome with you change the prediction with one opposing outcome, right? Basically, this is where you are in the confidence of your prediction, if you will. So here you're strongly confident that the branch is predicted taken because you've seen a lot of evidence for actually taken. Here, you're strongly confident that the branch is actually not taken because you've seen a lot of evidence. So it will take more time to change your prediction. That's why these are called strongly taken, or strongly taken and strongly not taken. And these are called weakly taken and weakly not taken states. Okay, basically, you change the prediction after two consecutive mistakes if you're in a strong state. You change the prediction after one consecutive mistake if you're in a weak state, if you will. So there's a good question. Is there some optimal size for a saturating counter? 2-bit seems too small. Well, this is actually, people have studied this empirically many times. I've done it actually, some of these studies during my PhD. So it's very difficult to decide on an optimal, because it's not just about, because hysteresis is sometimes bad, right? Sometimes you want to change your outcome quickly also. It's not also about the size of the counter, how you actually distribute the taken and not taken states as well. So I would say it's very hard to find an optimal. It really depends on the branch behavior in the end. You're very much workload dependent here, but that's a very good question to ask, basically. Is this the best machine you can build? Probably not. People have used 3-bit counters also, as we will see later on, and you may actually decide to use some other number of bits as well. Okay. So basically, 2-bit counter-based prediction. In this case, each branch is associated with a 2-bit counter stored in the BTB. One more bit provides hysteresis, and a strong prediction does not change with a single different outcome. So now let's go back to this other branch that we looked at. We had, remember, n iterations. So accuracy for a loop with n iterations it used to be n minus 2 divided by n. Now it becomes n minus 1 divided by n. So you basically make only one mistake in a loop in a loop branch. And you can think about why that is the case. I'll let you think about that, because you don't change the outcome once. You change the outcome when you see two opposing outcomes. You change the prediction when you see two opposing outcomes. Let's take a look at the special case over here. So assume that the counter is initialized to weakly taken. So this is predicted correctly. If it's weakly taken, and if the first instance is taken, you go to a strongly taken state. So in the next fetch of the branch, you will predict it as taken. The outcome will be not taken. That's fine. You will get back to a weakly taken state. In the next instance of the branch, you'll predict the branch as taken again, because now you're in the weakly taken state, and the outcome is taken. So you'll go back to the strongly taken state. In the next instance of the branch, you'll predict the branch as taken again because you're strongly taken, but the branch is not taken. So you'll go back to the weakly taken state. So you will always predict this branch as taken, assuming the counter is initialized to weakly taken. So you will get 50% accuracy, right? And you can do the same thing for a loop branch with n iterations. Here, n is equal to 2, actually. This is a special case of n where n is equal to 2. So this is much better than what we did with last time prediction, as you can see, right? 50% accuracy is quite good. Okay. So we get better prediction accuracy, as you saw. Of course, the downside is now we have more hardware costs because we have 2 bits per counter, and we need to have update logic for the counter, right? We need to be careful about how to update it clearly. But counter can still be part of a BTB entry, as we discussed. Okay, now I'll ask you the question, is this good enough? And basically, I will give you the answer. It's not good enough. We're going to do the analysis that we have done earlier. Let me see if there's any question over here. Okay, if you're starting in a weak prediction state and then always encounter the opposite of the prediction, it actually only works on the counter. Okay, I don't really fully understand it. But basically, starting state matters, yes. Starting state certainly matters. If you had started here, for example, as weakly not taken, then this wouldn't have worked. Yeah, basically, if you start with a bad state, this wouldn't have worked. So starting states in the end will matter. Okay. Yes, okay. So basically, with this kind of predictor, you get 85 to 90% accuracy for many programs with 2-bit counter-based prediction. As I said, this is also called bimodal. The question is this good enough? So how big is the branch problem, basically? So let's take a look at our exercise again. We have 20 pipeline stages, 5 instructions we fetch in a given cycle. 1 out of 5 instructions a branch, and each 5 instruction block ends with a branch. How long does it take to fetch 500 instructions? With 100% accuracy, basically it takes 100 cycles because we have 500 instructions and we're fetching 5, right? Now with no wasted work, with 90% accuracy, we mispredict 10 of those branches because we have 100 branches and 90% accuracy, and each branch caused us to spend 20 cycles on the wrong path. So which means that we need to actually fetch instructions in 300 cycles. So that's terrible, as we have discussed earlier. You fetch 200% extra instructions and IPC tanks. From 5 IPC, you go to 1.6. And that's 90%. Now, if you actually 85%, you get 300% extra instructions and IPC goes even lower. We're not even talking about data dependencies, right? That's just control dependencies. And 80%, which is respectable, you actually get 400% extra instructions and your IPC becomes 1. So basically, that's the importance of the branch problem. Even 80% or 85% or 90% is not enough if you have a deeper and wide fetch engine. And these are reasonable numbers today. So basically, the key question is going to be, can we do better? As we have asked many times in this course. And now I'm going to introduce the idea of 2-level prediction. Basically, this is going to use a different kind of history, 2 levels of history to predict a branch. So if you think about last time and 2-bit counter or m-bit counter predictors, they exploit some sort of last time predictability. Basically, they exploit the predictability of branches last n times, if you will. Last time is directly last execution instance. Not some n-bit counter looks at last n times or last 2 to the n times, basically depending on how you update the counters. You basically are looking at last n times or so. But people have realized you can do better. Basically, the first realization is very important. It's basically the idea of global branch correlation. A branch's outcome can be correlated with other branches' outcomes that you've executed in the past. And we're going to look at that. This is called global branch correlation. And the second realization is that a branch's outcome can be correlated with past outcomes of the same branch, but different instances of the branch, other than the outcome of the branch last time or last n times it was executed. So this is going to be important. This is called the local branch correlation. We're going to try to isolate the correlation within the instances of a branch. Okay, let's talk about the first one, because the first one is global and it's kind of surprising also. But as you understand the code, you will see that it's not that surprising because code behaves this way. And we're going to exploit something that happens in real programs. And real programs have the behavior that recently executed branch outcomes in the execution path are correlated with the outcome of the next branch. And I'm going to show you some examples. I'm sure you have programmed this way before, or something like this, let's say. If you look at these 2 branches, the first branch tests condition 1. And it's taken if condition 1 is true. The second branch is taken if both condition 1 and condition 2 are true at the same time. Now, if you know where the first branch went, then you have some information about where the second branch could go. So if the first branch is not taken, you definitely know that condition 1 is not true. Then the second branch should also not be taken, right? So if you somehow can correlate with the branch outcome of this prior branch, then you can basically do a good prediction for the second branch over here. So that's the beauty of correlating between the outcomes of different branches as you execute the program. Let's take a look at another example. Now, this maybe you have done something like this. If x is less than 1, you do something. If s is greater than 1, you do something. If the first one is taken, meaning if x is less than 1, then you know that the second one is definitely not taken, right? That's true for this more sophisticated example. If the first one is taken, you set a equal to 2. And the second one tests if a is equal to 0. So if the first one is taken, the second one is definitely not taken again, right? So clearly there's some correlation. If you know the outcome of the first branch, then you can predict with some confidence the outcome of the second. Not in all instances, but some instances you can definitely predict. Right? Another example, maybe more sophisticated. The first branch tests condition 1, the second branch tests condition 2, the third branch tests both conditions. And if the first branch, Y and Z, are both taken, then X is also taken because both conditions are true in that case. If Y or Z is not taken, then the X is also not taken because at least one condition is false in that case. Right? So you can come up with many, many, many examples like this. In fact, this is a very famous example from a spec workload. This is the benchmarking company, Spec Standard Performance Evaluation Corporation, that released benchmarks many, many times, the latest one being in 2017. In 1992, they released a set of benchmarks to evaluate microprocessor performance, and everybody evaluates their performance. And it turns out there's a set of branches that look like this in this particular program benchmark, equation to truth table. That's what EQNTOTT means. It generates a truth table from a Boolean expression, basically. But in the code, you have something that looks like this. And you can see that this code has some correlation. So the machines that did not exploit this correlation did not do well. But global branch predictors got built, and this benchmark did not become interesting anymore. Because basically, without global branch predictors, this last branch was very, very hard to predict. But with global branch predictors, this last branch became very reasonably easy to predict, let's say. Basically, if B is taken and B2 is taken, then B3 is not taken. And you can study that and look at it. I'm not going to go into more detail on this. But this is an example of how advances computer hardware can make some benchmarks irrelevant, if you will, or not so interesting anymore because the computer does really well in predicting the branches, so it's not a performance bottleneck anymore. Okay, so this is an anecdote that shows how global branch prediction actually has become very important over time. Okay, so how do we capture this, basically? Hopefully, now you're motivated. And this paper by Ye and Pat introduced the idea of global branch correlation and how to capture it, essentially. Basically, the idea is very simple. We have a history of branches, a history register, and we associate branch outcomes with the global taken and not taken history of all branches that we have seen. Of course, this history register is limited size, so it's not all branches, but it's the last n branches that were executed. Okay, so you basically make a prediction based on the outcome of the branch the last time the same global branch history was encountered. So you're not making a prediction based on the program counter only. You're really making the prediction based on the global branch history register, which direction the previous branches went. So program counter is not part of it right now. So you're really taking into account what happened to other branches. Okay, so implementation, one implementation of it, which is the most common implementations actually, you keep track of the global taken, not taken history of all branches in a register called Global History Register, GHR. I'm going to give you an example of this. And in fact, your book calls it, not book, the Scott McFarlane Combining Branch Predictors Technical Report that I assigned as reading calls it Global Register. It's the same thing. And you use the Global History Register to index into a table that recorded the outcome that was seen for each global history register value in the recent past. Basically, for each global history register value, you have an outcome. It could be a 2-bit counter. It could be a 1-bit counter. We're going to use 2-bit counters. And that was essentially the outcome that we saw the branch took last time this global history was seen. So we're basically correlating the branch outcome with the global history register value, if you will. This is the second table. Is called the pattern history table. It's essentially a table of 2-bit counters. But again, 2-bit. It could be 1 bit, it could be 3 bits, etc., as we discussed. So this is called the global history or global branch predictor. It uses 2 levels of history because you keep 1 level of history in the global history register. These are the directions of n branches, last n branches. And also you keep history in the pattern history table, the table of 2-bit counters, essentially which outcome we have seen when we saw that global branch history last. Essentially, we're matching a pattern. Whenever we saw this pattern of history register last time, this is what happened to this branch or whatever branch we were executing. And we're going to use that pattern, memorize that pattern, and use that as a prediction in the future. So let's take a look at the implementation of it. Basically, the first level is a global branch history register, n bits. This is the direction of last n branches. So let's take a look over here. Let me try to get my annotation because that may be actually easier to see, the spotlight. Okay, so basically you can see that let's say this is 16 bits. I just made it up. And these are to the 16 entries in pattern history table then. You can see that we basically have the history, taken, not taken history of the last 16 branches, and we shift in the history bit of the last branch from the right to the left, and we shift out the history from the left, the oldest history. So this is the direction of the immediately previous branch. It was not taken, let's say. This is the direction of the previous branch. It was taken, and then you basically go up to 16th previous branch. It was taken in this case, and you basically use this to index this pattern history table. And the pattern history table is a table of saturating counters for each history entry. It basically encodes the direction the branch took the last time the same history was seen. So the last time we saw this 1, 1, 1, 1, 1, 1, 0 history, we have a 2-bit counter that records whether you should be strongly taken, weakly taken, weakly not taken, or strongly not taken, basically, similar to the 2-bit counter prediction that we discussed. And you basically update the prediction based on what happened to the branch that you fetched with this history, essentially. So you basically update the counters the same way we discussed for 2-bit counter prediction. If the branch is predicted taken, but you had but the outcome is actually not taken, then you basically move to a state or weakly taken state, or either weakly taken state or weakly not taken state, depending on which state you start with, right? So hopefully this idea is very clear. And I already showed the 2-bit counters. And your McFarlane paper actually has a nice example of it. I'm not going to go through this in detail, but I'm going to give you the basic insight over here. You can see that if you look at a simple loop over here, there's an outer loop which iterates for many iterations, 100. I would have put more iterations over here, but fine. Basically, it's taken most of the time, 99% of the time, right? The second inner loop iterates basically 3 times, as you can see over here. So basically, after the initial startup time, the conditional branches have the following behavior, assuming the GR or global history register shifted to the left. So let's take a look at this last branch over here. After the inner loop is executed at least once, you test I equals 100, and the previous branches that tested J are actually taken, not taken, and the branch before that was actually taken, which is actually the loop branch, the outer loop branch. So basically, your global history for 4 branches should be taken, not taken. So you can see the not taken one over here, 0, taken 1, 1, taken 1, 1. What's not shown here is actually the previous instance of this outer loop branch that was also taken, because it's taken most of the time, as you can see. So the global history register that you see when you actually try to fetch this loop branch, outer loop branch, is 1110. And the outcome is usually taken because you fall through this branch only after the 100th iteration, right? Okay, so this branch tests I, as I said. Last 3 branches test J. That's why you have this history taken, not taken when you actually fetch this branch. You predict taken for I because it's usually taken. That's how the counters get updated over time, clearly. And the next history will become taken, not taken, because this is going to be taken. And the next history is going to be 1101, taken, not taken. And you're going to predict this J branch. And it's going to be taken for sure, right? So at this history register, whenever you see this history register value, it's going to be definitely taken. Whenever you see the next history register value, 1011, that's also going to be taken because the inner loop is taken definitely at least twice. The third time it's tested, it's not taken. So whenever you see this history 0111, it's going to be not taken. So by what the global branch predictor here is doing is associating histories, global histories, with different instances of different branches. So 1110 is always associated with the outer loop branch. 1101 is associated with the first iteration of the inner loop branch. 1011 is associated with the second iteration of the inner loop branch. 0111 is associated with the third iteration of the inner loop branch. And you can see that the results are definitely taken, not taken here. And this is usually taken. Over time, you figure out what happens, and you're almost always accurate, basically. You're definitely always accurate for the J branches, inner loop branches. You'll make a mistake once for the I branch. Of course, assuming this is done after everything is warmed up, let's say, right? So there's one question. How many branches can a modern history register keep track of? So 16 is a good number, but we will see. 16 is a good number. This is 4 in this case. Pentium Pro was 4, actually. But we will see. We're going to actually make it even more bigger in some cases, as we will see. So are the values only entered if they repeat a lot of times? Or what's the reason there's no value for I? So the reason there's no value for I is basically you always see 1110 whenever you execute I, and for all values of I, you see the same global history register value. Okay, so basically you shift in the last outcome as we have seen. Okay, so this idea of global branch prediction is actually implemented in the first widely commercially successful out-of-order execution machine, which is Intel Pentium Pro. It has a 2-level global branch predictor. It has a 4-bit global history register, just like what we have seen over here. And it has multiple pattern history tables. Basically, instead of having a single pattern history table, they use 4 of them. And which pattern history table to use is determined by the lower order bits of the branch address. So they basically want to reduce the interference between different branches so that they can get better prediction accuracy. So clearly you have a design choice in terms of how you organize these tables. Okay, there's one more question that I missed, I think. Do we have such a pattern entry for every possible entry, or do we organize them in a cache and only have the most recent patterns? So that's also a very good question. So in the implementation that I described over here, you have a single entry. Okay, here, you have a single entry for every possible value of the global history register. So if the global history register is n bits, you have 2 to the n entries over here. But again, as we will see later on, this may be very costly if n is large. So you may want to actually organize in a different way, like a cache, as you said, and existing more sophisticated branch predictors organize it that way. We'll talk about the Tage branch predictor. It is essentially tagged tables, the way you mentioned. So these are very good questions, actually. Okay, so I've given you the Pentium Pro branch predictor also. Now let's talk about this now. So clearly there's a reason why this works, and people have tried to analyze why this works also, actually. This is a beautiful paper that discusses how this correlation works and why 2-level branch predictors work. And they analyzed and they figured out that whenever you look at many branches, only 3 past branches directions really matter. So you're trying to predict branch X. You need to find 3 branches in the past history that really matter. But of course, these 3 branches differ for the different branches that you're trying to predict. So we have a large global history register, 16, for example. You may have 1 branch that correlates. If you make the global history register length 512, you look at 512 outcomes of prior branches. Maybe you capture these really 3 correlated branches. But again, you don't know which location those 3 branches are. That's why you need to have a large branch, global branch history register. So if you're interested, you can actually look at this paper, and some of the code examples that I took are actually from this paper also. Okay, to improve global branch predictor accuracy, people have actually added more information. Essentially, one improvement is to add more context information. So if you look at the global branch history register, we just use the global branch history register, GHR, to index the table. We don't use program counter information. So people realize that, okay, program counter information is also valuable. So why don't we hash these 2 types of information so that we can have more information about which branch is being predicted? That's the idea of the G-share predictor, which was actually introduced by the paper that I assigned you, combining branch predictors paper. GHR is hashed with the branch PC. And the idea looks very simple, as you can see over here, right? You don't just use the branch address. You don't just use the global history register, but also use the branch PC program counter, XOR them in some way, and then index into the pattern history table. This way you take into account more information. So there are multiple benefits to it. You use more context information. You don't lose the program counter context. And you also get a better utilization of the 2-bit counter array. So this is also important, actually. So this way you can actually utilize your 2-bit counters better. Another way actually is basically you can use different hashing functions over here, not necessarily just branch address, but branch address clearly distinguishes branches with different addresses. Of course, the downside is whenever you add this sort of thing, you add latency to the branch predictor. Now, this XOR may not be that much latency. We will see branch predictors that are actually much more higher latency soon. But keep in mind that this is an important part of the program. Somebody asked why XOR, for example. That's a good question. XOR is actually a good function to incorporate information from both address, branch PC, and the register. But of course, again, you can actually have shifting and XORing together and different kinds of information. And XOR is also very simple to implement, I should say. It's just a single bitwise operation, right? Okay, so let's review the 1-level branch predictor before we take a break. Essentially, now we have a direction predictor and cache of target addresses, as we've seen. 1-level branch predictor was using program counter to decide the direction, and the rest is the same. 2-level branch predictor global history branch predictor, use the global branch history to decide the direction, and use the program counter to actually get the target address. G-share predictor uses both information, global branch history register and program counter, to actually decide a prediction direction, as you can see. Okay. So I think this is a good time to take a break. But what is to come after the break is we realized that we can actually improve predictability using global branch correlation. In the right after the break, we're going to look at the second realization, which is branch itself is correlated with prior outcomes of itself as well. So we're going to exploit this local branch correlation. And then we're going to see that you can actually combine these different types of correlations in a hybrid branch predictor. And then later, we're going to look at more machine learning based predictors and get into the state of the art, where we discuss both machine learning as well as human heuristics taken to the next level, if you will. But let's take a break for 10 minutes. Let's be back at 15:20, and then we're going to continue our journey in branch prediction.
Okay. Okay, let's get started for the second half of the lecture. Remember, we talked about global correlation between branches, and I think this is a very cool idea to learn, essentially understand that correlation. Now let's talk about the local branch correlation, which is a different form of correlation of the branch with its own prior instances. Essentially, a branch's outcome can be correlated with past outcomes of the same branch, in addition to the outcome of the branch last time it was executed. So we're going to look at longer histories than just last time the branch was executed. And the best way of motivating this is actually how the paper that I assigned you does it. They actually talk about local branch correlation first, because it's maybe more intuitive to people. But basically, you can see there's a branch over here, the for loop. It iterates 3 times, it's taken 3 times, it's not taken once. And you can read over here, basically, if the loop test is done at the end of the body, the corresponding branch will execute the pattern 1, 1, 1, 0 to the n, where 1 and 0 represent taken and not taken respectively, and n is the number of times the loop is executed. Clearly, if we knew the direction of this branch had gone on previous 3 executions, then we could always be able to predict the next branch direction, I should say, correctly over here. And that's the idea, basically. The idea is to keep track of the history of each branch separately in this case, so that that history does not include taken or not taken outcomes of other branches. We just want to look at the local history of this branch. And it's kind of, it's somewhat, it's not exactly the same as the 2-bit counter prediction. 2-bit counter prediction keeps track of some history of the branch if you just use program counter, right? But right now we're looking at the history itself to index into a table of 2-bit counters. So let's take a look at this, basically. Essentially, to predict the loop branch perfectly, we want to identify the last iteration of the loop. And by having a separate PHT, pattern history table entry, for each local history, we can distinguish different iterations of a loop. And this works for short loops. And that's the idea. Basically, if you look at loop closing branches history, this is what happens. You get 0, 1, 1, 1, and the pattern history table says whenever you see that history, it should be not taken. And whenever you see other histories, it should be taken. So there's only one history where this branch should be not taken. So this is not, at least very easy to accomplish in a 2-bit counter or an n-bit counter machine, n-bit counter state machine. You really need to know the history of which previous directions this particular branch went to identify the loop closing branch. We will later talk about loop branches, which try to do this in a different way, but this is one reason why these local history works. There are other reasons why this works, which I'm not going to get into right now. But to capture this correlation, you want to have a per branch history register, essentially. Instead of having a global history register that incorporates taken, not taken outcomes from all branches, let's have it per branch or per set of branches, since per branch could be impossible, right? Because you may have many, many possible program counters. So basically, we associate the predicted outcome of a branch with taken, not taken history of the same branch, and make a prediction based on the outcome of the branch the last time the same local branch history was encountered for that branch. This is called the local history or local branch predictor. It uses 2 levels of history still, different from the n-bit counter predictor. And the first level of history is the per branch history register. And the second level of history is the history at that history register value, meaning last time this history register value was seen, was this taken or not taken, or is this going to be strongly taken or weakly taken, etc. So the same thing that applies to 2-bit counter predictors or n-bit counter predictors applies on a per branch history register value, if you will. And it looks like this, basically. It's similar to global history register based prediction, except now you have local history registers, right? So basically, the first level is a set of local history registers. Each of them is m bits. And then pattern history table is 2 to the n bits in this case. Basically, you select the history register based on the PC, program counter of the branch. And the second level is a table of saturating counters for each history entry. And this is the direction the branch took the last time the same history was seen. So clearly, this is a lot of cost, right? So for each branch, you have a local history register, right?
And you can see that basically indexing is the same, and we have 2-bit counters in the pattern history table. So you can go through this in your reading assignment as well. It's very simple once you understand the global history register predictor, except now you need to keep local history. So this is what it looks like, basically. You have a 2-level local history branch predictor. Now we use the program counter to index into these local history registers, pick the local history registers we want, essentially which directions earlier instances of this branch went, as opposed to which directions earlier instances of any branch went. And we use that to index into the direction predictor, which gives us perhaps a 2-bit counter-based taken or not taken prediction, given what happened in that history, right? For that branch in a previous instance of that history, right? Okay, so hopefully that's clear. Somehow we got out of the presentation. Now we're back. This gives you good local prediction accuracy. And I'm not going to give you numbers with it, but this paper that introduced both these different types of predictors, actually generalized them also, two-level adaptive training branch prediction, a seminal paper that has influenced all the machines that came afterwards, actually, categorizes the two-level branch predictors. The global history register can be global. And then you may have a global pattern history table. This is what we discussed as the global predictor. It's actually categorized as global branch history register and a global pattern history table. And the counters are adaptive, meaning they change dynamically. They're not set statically. Well, that's what we assumed with dynamic prediction earlier. But again, you can make it static also. The compiler can potentially set these counters depending on the histories. Of course, that's a difficult task for the compiler. So this is one example. This is the global branch predictor. This is another example, local branch predictor. Actually, I should choose this one, perhaps. I should choose PAG. But basically here, per address branch history registers you have, like earlier. And we also have a global pattern history table, as you can see over here. And we have adapter counters over here again. So you could argue that when you have per address branch history table, branch history registers, it doesn't make sense to have a global pattern history table because now different branches interfere with each other in the same table. And you would be perfectly right to say that. So maybe it makes sense to actually have many tables, multiple different tables. Maybe you do it per branch. Per branch is expensive, as I said. Maybe you do it per set of branches indexed by a portion of the program counter. So that sort of predictor makes more sense, actually. In real life, you see that sort of predictors as well. In fact, Intel Pentium Pro predictor was at a global 4-bit global history register and not a single global pattern history table. It had 4 pattern history tables, and you would select the pattern history table based on the value of the program counter. 2 bits in the program counter would decide which pattern history table you select. So you use some information from the history, and you also use some information from the branch that you're dealing with. So that was a global predictor. But local predictors can also be done in similar ways, which I'm not going to go into. But if you're really interested, I would recommend looking into this paper, which influenced all the machines that came after. So, of course, we don't stagnate. The question is, can we do better always, right? And we're going to do better, basically, than this as well. So we've seen different kinds of predictors that exploit different types of predictability in branches. And predictability of branches actually varies. Some branches are more predictable using local history, like the loop branches we have seen, or short loop branches. If you have a long loop branch, meaning if a loop iterates 500 times or so, it's not easy to capture that long history with a local predictor. Maybe you need to have a special predictor for this, as we will see in a little bit. But if you have short histories, maybe you can actually predict that nicely with local history. Some branches are more predictable using global history, and we've seen many examples of this from code. I think those are even more intuitive, if you will. For some others, a simple 2-bit counter is enough. Yet for others, a single bit is enough because they're highly biased. In fact, the compiler can do a good job. For example, if you have an error checking branch, if you check whether a pointer is null, probably you're not going to take that branch unless something is wrong with the program, especially if it's error checking null. If it's at the end of a linked list or so, maybe it depends on how the access pattern is, how your linked list is. But if it's an error checking branch, you can be sure that you're not going to take that branch unless there's something wrong with your program. So you can use a single static bit for that. So basically, there are different types of predictability for branches. And the people have observed this, of course. And researchers said, clearly there's heterogeneity in the predictability behavior of branches. So why don't we actually do something heterogeneous? Meaning there's no one-size-fits-all branch prediction algorithm for all possible branches that we'll see. So why don't we exploit this heterogeneity in predictability by designing heterogeneous or hybrid branch predictors? So there's one question: how does the machine know which prediction mechanism to use, assuming that multiple are implemented? So wait for some time, and hopefully we will talk about that. You can dynamically choose using a set of counters based on which predictor is doing better, for example. That could be one way. Or you could use programmer hints as well, potentially. But there could be multiple ways, basically. You will see one way soon. So this brings us to the idea of heterogeneous or hybrid branch predictors. Whenever you have two different types of behavior, and you cannot design a single mechanism that's one size fits all to many different types of behavior, at least two different types of behavior, then you may want to consider making things hybrid or heterogeneous. Heterogeneity is always useful to fit different types of behavior, basically. One size fits all usually doesn't work in those cases. And the idea, again, is basically the high-level idea is heterogeneity or using hybrid branch predictors. Basically, we want to use more than one type of predictor, multiple different algorithms to select the best prediction. For example, we want to use a hybrid of 2-bit counters and global predictor. We want to use a hybrid of 2-bit counters, global predictor, and a local predictor. And maybe we may want to use multiple different types of global and local predictors and a single 1-bit counter predictor and a profile-based predictor from the compiler, right? So you could actually, you could actually be creative in terms of how you organize this. Of course, the big advantage is now you get better accuracy because different predictors are better for different branches. Hopefully you pick the right one. That's a very good question. How do you pick the right one? We will discuss. But there's another benefit you get actually. And it's the reduced warm-up time. What does this mean? Basically, if you have long histories, it takes a long time to basically learn or memorize what happens in those histories. So you need to see many histories to basically warm up the branch predictor. But until a more sophisticated, longer history branch predictor warms up, you can use a slower warm-up predictors. Basically, slower warm-up predictor because that's already warmed up. For example, a compile time branch predictor is already warm, right? You get a single bit saying this is the likely direction. If your other predictor is not good enough yet because it has not been trained, let's say, over time, you pick the compile time prediction. Of course, the disadvantage is you should figure out how to pick which predictor to use. And if you don't do a good job, this may be bad, actually. So there needs to be a meta predictor or selector to decide which predictor to use. And of course, since we're adding more hardware, I should also add more hardware over here, clearly. We're actually getting longer access latencies, right? Because as you will see, we need to predict using multiple structures. We need to decide which one to use. So we have multiplexers to choose which predictors to use. But that said, these hybrid predictors actually have been implemented in many, many processors. In existing processors, actually, all we have is hybrid predictors. This went fast. This is one example from Alpha 21264. It's called a tournament predictor. It's essentially a hybrid predictor. But you can see, let's take a look at this example. So they had a minimum branch penalty of 7 cycles in that machine. Not a whole lot compared to today's machines, but typical branch penalty was higher due to out-of-order execution. And they store the target addresses in a BTB. Actually, it was iCache, part of the iCache for them, instruction cache. And they reset the predictable tables on a context switch. So I would recommend looking into this paper, which I'm going to recommend later on. Actually, it was an optional recommendation. It's a beautiful paper that describes the Alpha 21264 processor. But look at the branch predictor over here. Essentially, it's called a tournament predictor because it runs a tournament between different types of predictors. A global predictor over here and a local predictor over here. And you can see global predictors as exactly what we looked at. It has a 12-bit global history, and it has a one single global pattern history table. So 12-bit means 2 to the 12 entries, 4096 entries. Each entry is 2-bit counters. And it gives you a global prediction based on the history at that point in time. Local predictor, you index it with the program counter, get a local history register like we discussed. Local history register, they determined that the good size would be 10 bits in this case. And you can see that there are 1024 of these local history registers. And since the local history register entry is 10 bits, you have 1024 local pattern history table entries. And you can see that they have 3-bit counters over here. So they want to have some hysteresis in the local predictor for whatever reason, because they decided that you needed more hysteresis apparently in that case. And this you get a local prediction as well as a global prediction every single fetch cycle. And then you need to decide which one to use. And they have a choice predictor for this purpose. And basically choice predictor at the high level, it keeps track of which predictor was correct. And based on which predictor was correct over time, it decides to use that predictor. So for example, you index this choice predictor using the global history as it's shown over here. If the predictor, if the global predictor is correct historically at that history, then you choose the global predictor. If the local predictor is correct historically in that history, then you choose the local predictor. So this is one way of doing the prediction, of course. And this is not necessarily a very sophisticated way, but this is one way. And this may not be the final way. that is implemented in Alpha 21.264, but this is close enough to the final way. Essentially, you need a different mechanism to decide what predictor to use. And this is trained based on which predictor makes the correct prediction or the wrong prediction. So you need to update in a different way, essentially. Okay, so hopefully this gives you an idea of the complexity of existing branch predictors. And this is not where we ended. Remember, this is 1990s. We're going to talk about now 2000s and later. But one thing I should also talk about is biased branch as branch filtering. So it turns out many branches are biased in one branching. For example, 99% taken. The problem we see with this sort of branches, these branches pollute the branch prediction structures. What does this mean? This means that they make the prediction of other branches, other more difficult to predict branches, more difficult by causing interference in the branch prediction tables and history registers. So these are really easy to predict. But if you use the same structures as other branches go through, they actually pollute the branch prediction structures. So they make the hard to predict branches potentially even harder to predict. So people have realized that. And people have actually realized that you should really detect such biased branches and predict them with a simple predictor. So there's a detection method that's proposed, which could be similar to basically this choice predictor or biased branch predictor, if you will. You basically try to figure out which branches are biased based on the program counter. And if a branch is very biased, you say, I'm going to predict the bias based on whatever bias I figured out for this branch. I'm not going to make it participate in other structures. And this is very, very important, actually. If you want to make your branch predictor very, very successful, you got to get rid of the easy branches so that easy branches don't make your life difficult in predicting the hard branches. So you really want to, in other words, you really want to focus your effort on very hard to predict branches as opposed to using your sophisticated branch predictor for easy to predict branches. Okay, so hopefully that's clear. Okay, so basically the question is, are we done with branch prediction? So hybrid branch predictors actually work well. They get more than 90% prediction accuracy on average in some workloads, of course. Some difficult workloads, unfortunately, suffer a lot, especially workloads that are very much dependent on the data that you fetch from memory, and you make a decision based on that, for example. GCC is one example. It's compiler. I picked this example because this is a spec benchmark for decades and decades. And people have tried to understand the instruction level parallelism with GCC. And if you have an unlimited machine with unlimited resources, the maximum IPC with tournament prediction you can get with GCC is about 9 with the tournament predictor that I showed you earlier. But if you have an unlimited machine, actually maximum IPC is much larger if you get perfect prediction. So branch prediction actually limits you significantly, even if you do this tournament hybrid branch prediction, as you can see on a difficult workload. So we need to do better, basically. So, and that's going to be continuously the theme over here. We need to do better. The question is, of course, how to do better. Now, let me introduce some predictors that try to do better. I've already discussed the loop branches, but basically today's systems, today's machines use specialized loop branch detectors and predictors, especially for loop branches with large loop iteration counts. So they try to figure out the largest loop iteration count, detect it and predict it. It works well with loops with small number of iterations. Like, for example, if the iteration count is a million or a billion, you don't care anyway, because probably you're going to predict it correctly if you know what you're doing, especially if you're using a biased branch detector, right? But if your branch prediction loop count is larger than your history register, let's say larger than 16, but smaller than some huge number that makes branch prediction for that branch not matter as much, like maybe 30, 40, 50, 60, you still want to predict that branch correctly, but none of your predictors work well. As a result, you may actually use the loop branch detector and predictor. And this was first used Intel Pentium M, which is a precursor to a lot of Intel Pentium core processor designs that are used today. I'm going to give you a picture of this. I'm not going to talk about this more. I'm going to introduce two other branch predictors that have really, in a sense, revolutionized the thinking in branch prediction and affected real hardware more recently. Perceptron branch predictor. Basically, the idea is to learn the direction correlations between individual branches using a very simple machine learning technique and assign weights to correlations. And then I'm going to introduce a hybrid history length branch predictor that tries to use different types of histories, different length of histories to actually capture different types of correlations and different history length correlations between branches. And both of these ideas are actually used. All of these three ideas are actually used in real machines today, as we will discuss. Okay, so this is an example of Intel Pentium predictors. So the left part is what really is important for us, the loop predictor. Basically, this predictor is able to figure out the count of a loop based on previous executions of the loop. And it basically sets the count when you get to the loop again, and assumes that you're going to take the loop the same number of iterations, assuming you have some confidence, which we will talk about confidence. And then it predicts the branch as not taken when you get to that count. Okay, well, which is the limit, basically, essentially. And basically, otherwise, it predicts the loop as taken, as the loop branch to be iterating. Okay, so basically, the assumption is that you're going to take the loop the same number of times that you have taken the previously, with some confidence built in, which I'm not going to talk about. And if this works for loops that are predictable, that's great. In fact, Intel reports that it works nicely, and there are papers that are written also that show that it works nicely. But if it doesn't work, if your loop branches are not predictable in this manner, then it's not going to be very useful. They also have indirect branch predictors that are reserved for branches that jump through registers, which we have not talked about so far. If we have time, we will, but we will probably not have time. You will have backup slides where you can look. So existing machines also have specialized indirect branch predictors. That's the point of this right predictor over here. And if you're interested in these predictors, you can look at this paper that was written by Intel that introduced the Intel Pentium M processor as early as 2003, as you can see. Now let's take a look at more advanced branch prediction. And I'm going to cover two algorithms, mainly perceptron and TAGE, if you will. So perceptron is interesting because this is perhaps the first very successful, and maybe the only very successful currently, application of a very simple machine learning algorithm in hardware, microarchitecture, let's say. And you may have studied perceptrons. Feel free to raise your hand or right if you have studied perceptrons. I'm actually curious if you study perceptrons at this time. But essentially, perceptron is developed in as early as 1958 by Rosenblatt. It's described in this book that talks about theory of brain mechanisms, etc. But essentially, it's a very simplified model of a biological neuron. Very simplified. It's not able to explain everything about a biological neuron as we know it today, of course, even at the time, actually. But the basic idea is it's performs some sort of classification task. So basically, given some inputs, it learns an input vector X and maps it to a 0 or 1. Okay, so you have an input vector X and you map it to a 0 or 1. Well, how do you do that? So you have a vector X, and you can learn the linear function, assuming a linear function exists, of how each element of the vector affects the output, classification output, 0 or 1, stored in an internal weight vector. So there's an internal weight that you assign for each input, and you multiply the input values with the weight, and then you basically decide whether the outcome is a 0 or 1. So let me give you an example that you could potentially empathize with. So language detection is one classification task. Actually, existing neural networks are classification tasks also. They detect whether something is a dog or not dog, for example, right? I like the language because you will see. But existing neural networks actually are much more sophisticated in the sense that they're not binary classifiers. They're actually usually n-ary classifiers. We will talk about that when we talk about systolic arrays a little bit. But essentially, if you want to detect a language, whether or not a language is German, the way you may actually want to train a network like perceptron, I shouldn't say network, train a perceptron is you basically give it some inputs, and the perceptron, let's say all of the words that you may encounter, and perceptron associates a weight with each word. And if this word is a German word, the weight is positive. If the word is definitely not a German word, the weight is negative. Okay. And you have, of course, a range for the weights, right? Weights. And basically, you train the perceptron by giving it weights of all the words that you encounter. And later, let's say you want to do a classification. And the classification task is this. I'm going to give you a word and or a set of words, essentially. And I'm going to ask you the question whether what you're hearing is German or not. And what you do is you get the set of words, you multiply that's your vector, essentially. The vector is the set of words that you have. You multiply it internally with a weight function, weight vector. And that output, the multiplication output, will be some number. Now, if it's greater than 0, then you say, okay, I'm confident that what I'm hearing is German. If it's less than 0, now you say, I'm confident that what I'm hearing is not German. If it's 0, maybe you're somewhat not decided, right? Maybe some words are German, some words are not German. So that's the idea, basically. Given some number of words that you get, we're trying to decide whether what we see or hear is German or not German. And we've already trained the network, trained the perceptron to learn the internal weights. Now we multiply the vector with the weights to get a result. And if the result is positive or strongly positive, let's say, strongly large number, positive number, then we say, oh, it's German, definitely not German. Otherwise, we say it's not German. Right? That's the idea, basically. This is one very simple classification task. Now we're talking about branch prediction. In branch prediction, actually, it's going to be something else. But let's take a look at this. So output is going to be weight vector multiplied by the input vector, just like we've done. You multiply each weight with the each word with the its weight, and then there's a potential bias that you can learn whether the general thing you're hearing is German. And then you test whether it's greater than 0. And if it's greater than 0, you basically classify it as 1, otherwise it's classified as 0, basically different classes. In the branch prediction context, we don't have words, but we have branch history register bits. So vector X is really the branch history register bits, and output is the prediction for the current branch. And the internal weight vector is how correlated the branch history register bits that we're examining is with the output of the current branch. Basically, if it's taken, then you have a strongly high positive weight. If it's not taken, if there's a strong correlation, you get a strongly correlates that's taken, then you get a positive weight. Otherwise, you get a negative weight. And we will see, I'm not going to go into details, but you can do the calculations also yourself. Basically, the idea is to use this perceptron to learn the correlations between branch history register bits and branch outcome. And this is the pictorial depiction of a perceptron. Basically, everything I said earlier applies over here. Essentially, Y is the output, W0 is the bias, and W1 is the weight vector that we have learned based on training, and Xi is essentially the input vector, vector X that I showed you over here. And then the output is basically bias plus the vector multiplication of X and W. Okay, so how do you do this in branch prediction? Each branch is associated with a perceptron. A perceptron contains a set of weights Wi. Each weight corresponds to a bit in the global history register, as we discussed, if it's a global perceptron. Basically, this weight represents how much the bit is correlated with the direction of the branch. If you have a positive correlation, you get a large positive plus weight. If you have a negative correlation, you get a large negative minus weight. Okay. And then in the prediction, when you're predicting, so you train to learn the weights, and there's a training function, which I'm going to show you in the next slide, but we're not going to go into detail. Like any machine learning algorithm, you need to have a training function so that you can do the classification correctly afterwards. But the prediction function expresses global history register bits as 1 and -1, taken and not taken. And you take the dot product of global history register and the weights. That's what this is over here. And then you may add a bias also, optionally, if the branch is biased, for example. Now, if the output is greater than 0, you predict it as taken. If the output is less than 0 or less than or equal to 0, you predict it not taken. So basically, you exploit the potential capability of learning of these correlations of the perceptron. So it's a beautiful idea. It's limited to the limitations of perceptron, but perceptron is easy to build in hardware, but we will see that this is even hard to build in hardware. And this is what it looks like, basically. With the branch address, you go into a table of perceptrons, you select the perceptron, and you basically compute the output by taking the dot product of the perceptron weights and the history register, and you make a prediction after you compute this output. That's the prediction function. And once you have the branch outcome, you train the perceptron, right? And training clearly tries to figure out the correlations based on which outcome the branch took, right? So you can imagine the training is actually very easy to understand, but I'm not going to go into it. But this is a single layer network, as you can see, right? So the bias weight could be the bias of the branch independent of the history, as we discussed. And you can see the dot product of GHR and global history register and perceptron weights over here. Okay, and the output is compared to 0 in the end. Now, this is a very simple single layer network, and it suffers from all of the disadvantages of a perceptron. But let's talk about the advantages first. So it actually leads to more sophisticated learning mechanisms, so it gets better accuracy. In fact, this is proven many times. In fact, it was implemented in the Samsung microarchitecture that's described in this paper, which I'm going to recommend you to take a look at if you have time. It enables long branch history lengths. It says better accuracy. Of course, this comes at the cost of some latency and implementation complexity. But now you can have very long branch history lengths, actually, or branch history register doesn't have to be 16, because you don't have a pattern history table in this particular case, right? You may have a 1,000 element vector over here, for example. But of course, the latencies will increase if that's the case. Now, this advantage is hard to implement. Even with short branch history lengths, this is not easy to implement. You now have an adder tree to compute the perceptron output to create the dot product. And it also has the disadvantages of learning, let's say, inaccuracies or deficiencies of perceptron. So perceptron can only learn linearly separable functions. Essentially, the output needs to be a function, linear combination of the weight and the input. And essentially, you cannot learn an XOR function, for example, which is not a nonlinear function, or any other nonlinear function. And this limits the accuracy of this approach clearly. Okay, but this is still a successful example of use of machine learning in processor design. And it was implemented in the Samsung processor. If you're interested, you can actually take a look at it. And it talks about perceptron-based branch prediction and a lot of the other things that we have talked about actually in microarchitecture. If you're interested, take a look. Okay, let me give you another idea that has influenced existing processors a lot. And this idea is actually a human heuristics-driven idea. It tries to accomplish some things perceptron tries to accomplish, but it's clearly not the learning part. Not the automatic learning part. It's more memorization, if you will. But basically, people have realized that you want different history lengths for different branches for better prediction accuracy. This has been realized for a long time, but people didn't know exactly how to build that predictor. More recently, this predictor, TAGE, was proposed. The idea is to have multiple tables, pattern history tables, indexed with different global history registers with different history lengths. So it looks kind of like this, basically. You have some basis predictor, which may be just indexed with PC, not even any history, as you can see. You have another table with short history, and you may also have a hash of PC. You have another table that's indexed with a longer history, another table with an even longer history, another table with an even longer history. So branches that require really, really long histories, thousands of bits, may be allocated over here. Branches that require short histories may be allocated over here. So it's an example of a hybrid branch predictor, actually, but the principles of working of each table look similar. And in fact, when it was proposed as a geometric history length branch prediction, so that you have geometrically increasing. The history lengths that are used are a geometric series, so that you can get to very high history lengths over here. And this enables you to really adapt the history length on a per branch basis. And it's actually a very nice idea. That way you can use the history length that fits the branch, if you will. And this turned out to be a very strongly accurate predictor compared to other hybrid predictors. And this is actually used in many processors, a variant of this. Not exactly this clearly. But let me give you the advantage and disadvantage of this. Basically, you choose the best history length to predict each branch, so you get better accuracy. It enables long branch history lengths, better accuracies. This is similar to perceptron, but maybe it's simpler to enable long branch history lengths this way, because whenever you increase the history length in perceptron, you need to increase the multiplication tree also. The disadvantage is hardware design complexity is not low. Maybe not as high as perceptron, because you don't do multiplications over here. You just have table accesses, but still it's not no. And you need to actually be very careful in the design. You need to choose very good hash function and table size to maximize accuracy and minimize latency in this case. But this is a successful recent idea that's actually used in many modern processor designs. In fact, modern processor designs use both perceptron and TAGE. And maybe the higher accuracy comes from the use of TAGE plus a lot of heuristics. And this is what this slide shows. This is close to the state of the art in branch prediction in existing processors. Of course, there's a lot that needs to be involved in it. It looks kind of simple when you look at it. But you can see that there's a main predictor. It could be TAGE. It could be perceptron plus TAGE. Okay. This main predictor gives you a prediction. And you basically apply some statistical mechanisms, different histories, global, local, and something called skeleton, which I'm not going to go into. Basically, you apply some mechanisms to statistically correct the prediction that you get. And you also look at the confidence, how confident you are in the prediction. So you basically use a lot of information to decide whether the prediction you're getting from the main predictor is correct or not. And then you overturn the prediction based on what you know otherwise separately from the TAGE predictor. On top of this, you have a loop predictor that you have as well, as we discussed. And you essentially have a hybrid predictor, and main predictor is actually a hybrid predictor by itself, as you can see. And we have PC and global history. You can see that every concept that we discussed is actually used in this predictor, including the confidence that we're going to see. And you may actually include perceptron in one of the algorithms over here, which I'm not going to get into. So existing branch predictors are actually quite complex, as you can see. And the latency may be high to do this prediction. And it becomes a very interesting art and science to actually design these predictors. Now, let me talk about confidence, since mentioned over here. I kind of implicitly mentioned confidence so far, but confidence is something that we as humans do, right? Basically, we predict something and we can say, oh, I'm really 60% confident that that's what I said is true, right? We can do the same thing with branch predictors. We can estimate if the branch prediction is likely to be correct, and depending on that, we can choose different actions, right? And this is called branch confidence estimation. It was actually introduced by the seminal paper in 1996. Basically, the idea is to estimate how confident you are in the prediction. So why do you do this? It could be very useful in deciding how to speculate. For example, what predictor or pattern history table entry or what table to choose or use. So actually, it's used, for example, in terms of deciding statistical correlation, and it's also inside Tage over here. And it could be useful in whether you want to keep fetching on this path. Maybe you stop fetch. Basically, you say, oh, I'm not confident, so I don't want to fetch to save power, right? Or whether you want to switch to some other way of handling the branch, like eager execution or predicted execution, which we don't have time to cover, but you can find on the slides. And slides also have pointers to some other lectures that cover these concepts. So basically, it can decide do something else, right? Based on, or which predictor to use. You can decide many things based on this confidence. So how do you actually estimate this confidence? Basically, the hardware can keep a record of correct or incorrect outcomes for the past n instances of the branch. And based on the correct and incorrect patterns, you can guess if the current prediction will be likely correct or incorrect. Again, there are many different design options over here. I'm not going to talk about over here. These are confidence registers, etc. But essentially, you would like to figure out whether you're doing, how confident you are in the prediction. And one example application is called pipeline gating. So if you look over here, if you have too many low confidence branches in the machine, meaning that you have fetched many branches in the machine and you're not confident in any of them, or you have too many branches that are not confident, basically you can say, okay, I'm going to stop fetch because it's likely that I'm on the wrong path anyway. So that's one idea. And that was introduced in this work, and some existing processors actually make use of this idea. And it's clearly a cool idea, right? And I'm not going to go into it right now. But in the remaining time, I'm very going to quickly handle some way of handling branches that also doesn't work. So we talk about branch prediction, which works very nicely, but I'm also going to give you an example of what doesn't work, and that's going to be delayed branching. And I think that we're going to stop right after that because we don't have time. But remember, we actually have many different ways of handling control dependencies. We talked about branch prediction a lot. We talked about fine-grained multi-threading. I'm going to talk about employing delayed branching, branch delay slot. Since we will not have time, you can take a look at predicated execution and multipath execution in the remaining slides, again, which have pointers to some earlier lectures. And you can also see there are some slides that talk about handling other types of branches, like return branches, call branches, or call and returns, as well as indirect branches. Indirect branches tend to be actually difficult. Okay, so delayed branching, a very interesting idea, but interesting idea that doesn't work. Basically, the idea comes from the philosophy of reduced instruction set computers. Basically, hardware should not do branch prediction. Basically, that's the philosophy. Software should do everything. So if we want to have a pipeline processor, why don't we change the semantics of a branch instruction such that you branch after n instructions? That way, you can fill the pipeline with n instructions and branch takes effect only after them. Or you can do this in terms of cycles. Now you can see that it's becoming very much dependent on the microarchitecture, right? So now you make the semantics of a branch instruction dependent on the microarchitecture of it. But that's the basic idea. Delay the execution of a branch. You have n instructions, delay slots, that come after the branch, and they're always executed regardless of the branch direction because the branch doesn't affect them. You're delaying the execution of the branch. Now, of course, the problem becomes, how do you find instructions to fill the delay slots? And this is very similar to the instruction scheduling problem that we discussed many times earlier. You need to be able to find independent instructions to fill the delay slots. Basically, branch must be independent of delay slot instructions, and you also run into a lot of issues in terms of which instructions you can move while being safe and correct. You should not violate any dependencies, basically. Okay. So if you have an unconditional branch, clearly it's easier to find the instructions to fill the delay slot because you can fill the delay slot with instructions from the target of the branch, right? Because the branch is going to jump there anyway, unconditional branch. So fill the instructions from the target locations of the branch, pick the end instructions and move them under the branch. That's easy. But if you have a conditional branch, it becomes harder. Condition computation should not depend on instruction and delay slots. And hence it becomes very difficult to fill the delay slot. So this is part of the problem with delayed branching. But let's take a look at some other problems also. So let me give you the idea with a two-stage pipeline, because existing ISAs have one delay slot. People said, okay, maybe we're going to have a two-stage pipeline. Bad idea. Clearly, we have lots of stages in our pipeline. But this idea may work in a two-stage pipeline, as you can see. So basically, if you have normal code that looks like this, these are instructions, A, B, C, conditional branch that goes to X, X is here, and then D, E, F. And then we have instruction fetch and execute. These are two stages. Now you can see that B, the computation of the branch depends on A and C, but not B. So we can actually move the branch B to the delay slot. But this is our normal code. Normal code execution, you fetch A. While you're fetching A, while you're executing A, you fetch B. While you're executing B, you fetch C. While you're executing C, you fetch the conditional branch and assume that you stall. Comparison point is stalling. Okay, it takes 6 cycles if you stall after this branch. Not bad because it's a two-stage pipeline. Now, if you have delayed branching, if you change the semantics of the branch such that the next instruction after the branch is always executed, you have to fill that slot with an instruction that the branch doesn't depend on and where you don't violate the data dependencies also. So B looks like a very good target. So you move B under the branch. And this works perfectly in this particular case. As you can see, whenever we are executing the branch, you can fetch B, and B is going to be executed no matter what direction branch takes. And that's true, actually, right? Because you have to execute B no matter what direction could this conditional branch takes, because it's before the branch, right before the branch. So this works perfectly in this case. That way you can reduce the timeline from 6 cycles to 5 cycles, as you can see. So this is a significant gain, actually, if it works. Now, the problem is this doesn't always work, first of all. So people have actually increased the sophistication of delayed branching, if you will. MIPS, actually, the processor you're designing has delayed branching. Unfortunately, let's say, as we will see in a little bit. But people actually looked at fancy delayed branching and so that they can fill the delay slot better. So at Spark ISA, for example, which is another example of this RISC philosophy, reduced instruction set philosophy, they have delayed branch with squashing. So the semantics looks like this now. If the branch falls through, in other words, it's not taken, the delay slot instruction is not executed. Otherwise, it's always executed. So you still have a delay slot, but you sometimes don't execute it. Now, this is becoming a little bit more complex, right? Because now, based on some condition that's dynamic, not taken branch, you're squashing some flushing, essentially, and a delay slot instruction. So why did they introduce this? Why could this help? Let's take a look at this code where you could not fill the delay slot with an instruction before the branch. So A, B, C, branch conditional X. X is a loop. Now we're looping, right? But you cannot fill the instruction slot, delay slot, HCX, with, this is normal code. But assume that you have a delay slot. You cannot fill the delay slot with any instruction before the branch, as you can see, because they're all dependent, right? So you put a no up. That sounds bad. So you're back to square one, even if you have delayed branching. So people have realized that you cannot fill the instruction delay, the delay slot with what comes earlier, but maybe you can fill it with the taken path. And that's the idea. So basically you fill the delay slot with an instruction from the next iteration. So you take instruction A from the next iteration, you put it into the delay slot. This works nicely if the branch is taken, because you're going to execute A if the branch is taken anyways, right? So this works nicely. But if the branch is not taken, now you should not execute A, because you're not going to go to the next iteration. That's why you need to squash it. Now you see the complications. This is a perfect example of a complication that you introduce when you tie the semantics of the ISA to the execution that happens in the pipeline, if you will, by adding delay slots. What if you don't have something to fill the delay slot with? You may fill it with some instruction by changing the semantics of the instruction again, but then you need to squash the instruction that you fill it with if it's not supposed to be executed. Okay, so let me cover the advantages and disadvantages of delayed branching, and we will be done. Essentially, as any idea, this has advantages and disadvantages, clearly. This keeps the pipeline full with useful instructions in a simple way. Clearly, it's a simple idea, but it relies on some assumptions to be true. And these assumptions are difficult to get right. First of all, number of delay slots should be the number of instructions to keep the pipeline full before the branch resolves. Who said that delay slot should be 1, right? In fact, a single delay slot doesn't help me much if the pipeline depth is 20, if the branch resolves after 20 cycles. I just fill 1. I still need to do something else for the remaining 19 slots. And you do branch prediction. So now the hardware designer needs to deal with the delayed branching plus branch prediction. That doesn't sound very good, basically. I would rather just do branch prediction and get it right, as opposed to deal with something semantically misleading, let's say, because the ISA is dependent on the microarchitecture, right? So all delay slots should be filled with useful instructions also, of course, right? If you want this to be to really perfectly work. So basically, this leads us to disadvantages. It turns out it's not easy to fill the delay slots. This should not be surprising to you when we discussed instruction reordering, right? Compiler has a difficult task. It's difficult to reorder instructions. Even with a 2-stage pipeline, it's difficult to fill the delay slots. And because number of delay slots increase with pipeline depth, superscale execution width, and number of delay slots should be variable with variable latency operations, because if you have a load instruction or a variable latency operation, you don't know how long it'll take, right? So basically, this makes it very difficult to fill the delay slots, but also you may need to recompile your code potentially if you change the semantics of your ISA based on the microarchitecture. As a result, people realize that this was a bad idea, basically, because you tie the ISA semantics to hardware implementation. And by adding 1 delay slot, you don't accomplish anything. You just make hardware designers' life harder, software designers' life also harder. And if the pipeline implementation changes with next design, you're not getting even more benefits going into the future. So this is an example where separation of concerns should be clean. ISA semantics, unless you are really full-blown and saying, okay, my ISA is always tied to microarchitecture, in a general purpose ISA, you probably don't want to do that because microarchitecture should be flexibly changed without being tied to the ISA. Otherwise, whatever you introduce into the ISA may not be very useful in general. And right now, you're left with a baggage in some of these ISAs where you have to implement the delay slot because the ISA specifies it, code is written for it, but it doesn't benefit you much. Okay, so there's an aside over here that talks about how to fill the delay slot. This is very similar to what we have discussed, but you can also actually fill the delay slot with if there's some other branch that comes after, or with the taken path and the not taken path. But actually, the difficulty is even higher because now you need to do static instruction scheduling, and you need to add fix-up code. You need to make sure that reordering independent instructions does not change the program semantics. So that makes things harder for the compiler also. So this basically, you need to think about whether what you're doing is safe and correct. So I will finish with the pointer to the static instruction scheduling lecture. This is something we are not going to cover, but a lot of things that we discussed rely on, or you can learn more about static instruction scheduling that may make the machines better. And you can take a look at this lecture or these lectures if you're interested. So this is where I'm going to stop. If you're interested, you can look at predicated execution and multipath execution, which are interesting ideas employed in some processors today, but we don't have time to go over them. But if you have any questions, I'm happy to take them. Otherwise, I will see you tomorrow. And tomorrow, we will actually cover very long instruction word architectures first, and then systolic arrays, which are ideas that have been very successful in different domains. And that's going to be interesting because VLIW, very long instruction word processors, are actually very much heavily dependent on static instruction scheduling. Okay, if there are no questions, I will leave you with this slide at this point, and I will see you tomorrow.